Introduction to Mechanical Modeling. By the end of this section, you should be able to create a free body diagram for simple 1 degree of freedom spring mass damper mechanical systems. You should be able to create the equations of motion for that single element mechanical system using the free body diagram. And then using the equation of motion, you should be able to find the closed form solution for the displacement of the mass in these spring mass damper systems. This unit, Unit 1, is going to really focus on the modeling aspect of system dynamics. Then we are going to use that model, which is going to be the mathematical description of the dynamics of our system, and conduct analysis in Unit 2 so that we can predict the behavior of our system. And then in Unit 3, Control, we are going to be modifying our system or modifying inputs into our system to get a desired behavior. So starting here in the modeling step, we want to look in general, what are we doing when we are making a model? And this is going to tie into partially in the philosophy of science, what are we trying to accomplish when we make a model? So we can start by looking at this quote, "All models are wrong, but some are useful." And I like to think of this in part as a guiding principle of what we're really doing as, well, scientists, engineers, when we are trying to describe the real world using a mathematical model, which is what we do in this course. So what is the point of what we're trying to do model-wise in this course? Well, in dynamic modeling, or we're modeling things that are evolving or happening over time, really in essence, what are we trying to do? We are trying to predict the future. What we're going to know is what is the state or the condition of our system now when time begins at 0. And then what we want to be able to do is turn the crank and move time forward and know in advance how our system is going to be behaving in the future. And this is going to be useful because we want to maybe control what that system is going to be doing. We want it to behave in a particular way, or maybe we don't have control over the system, but we want to know where are we headed as we turn time forward. In part, the modeling is going to be useful because we can just on paper or with the computer make predictions about how a system is going to behave. We don't need to actually build a system and then see how it's going to be behaving in real life if we have a model that describes that. And then the model is going to let us easily change parameters in our system or change inputs into our system and make the predictions of how it behaves without, again, physically building it, physically swapping out parts to see what the behavior looks like. Now, this is going to be pertinent to any type of dynamic modeling we're doing. We're going to apply this in this section directly into mechanical modeling, but through the course, when we look at electrical modeling and we look at fluid modeling, or outside of this course, if you look at biological economic systems, for example, once we can boil it down to the mathematical description, all of these ideas are still going to be relevant. So we want to predict the future. We need to be able to describe our system using math, in particular, differential equations for this course. Now, there are other sorts of mathematical models. You can use a purely statistical model. That's not what we're talking about in this class. We are using differential equations for the most part to make predictions about the future or model our system over time. Now, we are not, almost never, trying to make a perfect replica of reality when we are making our model. There's going to be many things that we don't account for when we make our model that we don't include, and we're going to neglect, and we're going to ignore. So for instance, when we're talking about mechanical systems now, a lot of times we're going to be ignoring, for example, air resistance in our system. Usually it's not going to really make a difference in the performance of our system. We're going to go at low enough velocities, or we're not going very far, and the cross sections maybe are relatively small, that we could include it into our system, but really the effect it's going to have on our predictive capabilities is going to be negligible. Now, in a different type of system, for example, if we want to model a parachute, well, in that case, kind of the premise of the parachute is that it operates under air resistance. So in a scenario like that, ignoring the air resistance is not going to be negligible, and it's kind of the whole point of the system that we are modeling. But also in these mechanical systems, aside from, let's say, air resistance, we also are neglecting maybe some microscopic things. We are going to be ignoring very minuscule things that might be affecting our system. We are not going to be modeling van der Waals forces between our object and the ground. We are not going to be modeling the very slight magnetic pull that the Earth's magnetic field might be having on ferromagnetic parts of our system. So all these things indeed are certainly there. They are certainly applying forces and moments in the system. But by and large, these types of small things are going to be so small of their impact on our system that we can just ignore them. Again, are we going to be making a big difference ignoring these? No, but we are not capturing that exact replica of reality. And that's going to be okay as we go look forward. We're also going to simplify relationships that we have in our system. So, for example, in these mechanical models, when we are looking at springs and dampers, for instance, we, for the most part, are going to be assuming a linear relationship between the force in our spring and its displacement, or the force in a damper and its velocity. In reality, no spring, no damper actually has that perfect linear relationship between the force and its displacement, or its force and its velocity. But in the region that we are typically operating these springs and dampers, a linearization or a linear relationship is going to be sufficient. It's going to be close enough for what we're doing. If we're operating with a spring that really isn't linear in the region that we want to use it, then probably it will not be appropriate to make that linearization or that linear assumption about its behavior. And certainly there are nonlinear springs, like leaf springs, that we might be interested in using. And we'll talk about that later in the course, but for now, the springs dampers we use, we're going to be perfectly fine using that linear relationship. Now, why are we doing this? Well, one, we cannot account for everything. There's going to be things that when we are modeling that we knowingly are going to ignore, for instance, air resistance. So we have kind of these known things that we are ignoring. We also have things that we might not even be realizing that we are ignoring, and definitely in complex systems, this is going to come up a lot more often. And these things that we're ignoring, maybe without knowing it, sometimes have very little effect on our system. And then if we test our system versus reality and it comes out very close, maybe we didn't even realize that we were neglecting these outside forces, these outside moments. And then there's going to be things in our modeling that affect our system that we were not even aware of when we were building the model. So when we go to validate our model versus reality, it might not come very close to it because we ignored something that we didn't even know we were ignoring. But ignoring these things, we are typically doing it for two reasons. We want to simplify the math in our problem. So for example, when we use a linear spring or a linear damper, it's going to be much easier to solve these systems when we have a linear relationship between force and displacement, for instance, rather than a quadratic or some other type of relationship. It's going to keep our ordinary differential equations linear, and we know how to solve those much better than when we have a nonlinear ordinary differential equation. And as we remove terms, by making these simplifications, we are also just, again, making the model easier to understand if we're looking at really the key features of our system that are really going to impact its dynamics, and we're not being bogged down by all these very small, negligible pieces that have very little impact in the behavior of our system. Really, what are we trying to do? Can we make a model that is going to give us the general behavior of the system? Really what's going to come down to is the model we're making useful to make predictions with? And is the error from the reality when we validate our model versus the real world going to be sufficiently small? And here small is in quotes because it's really going to be relative to the problem that we're looking at. What do we consider a small amount of error? So once again, if we're ignoring air resistance in our model and then we are validating our model versus real life, probably it's not going to introduce a lot of error what our model predicts from what the real life behavior of our system is. So in most systems, probably it's going to be fair to ignore that. But again, if it's a type of system where it's a non-negligible effect, like the parachute again, If we ignore that air resistance and we try to validate our model versus real life, we're going to see a lot of error between what our model predicts our parachute is going to do and what it does do in real life. So we need our models accurate enough that it is useful for prediction. And that circles back to kind of the quote that is going to introduce us into modeling. All models are wrong, but some are useful. So we are interested in making useful models that simplify reality in the correct way.